And so our first speaker this morning in our session on the potpourri of craters from the Moon series is Rachel Fry, who will be talking to us about testing a standardized schema for geologic mapping on impact craters. Take it away.
Thank you, Cassie. Yes, my name is Rachel Fry. I am with the USGS Astrogeology Science Center's Planetary Geologic Mapping Group. As Cassie said, I'm going to be talking about how we developed and began testing a standardized schema for mapping impact craters on geologic maps. So this project was conceptualized in 2019, 2020, and it was put on hiatus during COVID and then was initialized earlier this year when I came onto the project. And as I was going through some of the documents from this project, there's this one document that had these some of these lines that I'm going to show my nerd cred here, I think are beautiful. One of those is this in that's italicized here. The subtle strength of standards is shown by users who intuitively understand a map without needing discipline expertise. I thought that was a very poignant line and really highlighted how when most people, whether they're scientists or not, pick up a map, for the most part, they can figure out what they're looking at. Even a geologic map, it may take a little bit of like finagling. Oh, there's the legend. Okay, cool. But I know what I'm looking at. Geologic maps are inherently cross-disciplinary. They bridge this knowledge across all disciplines. I note here specifically geomorphology, geophysics, geochemistry, geochronology. They take these 3D structures and temporal structures and features, and they compress them into this two-dimensional format. And all of that is enhanced by these standards and standardized cartography that is used in most maps. So craters, planetary mapping has been done for what, 5 decades now, and things have changed with technology, with our techniques, with the data over these 5 decades. And so the way that we map features and the focus of this one, obviously, impact craters, has changed over that time. And people, have mapped throughout these 5 decades differently, but also I find myself mapping things like impact craters differently based on how I feel that day. So creating a standardization, I think, is a really robust thing that helps make maps something that can be this is one of the other things I'm going to talk about. We can start to compare them across scales and planetary bodies, and that makes them much more robust products. So one of the other things is we've begun really understanding impact crater processes is understanding what actually is shown in an impact crater, the geology. So the geology that's shown on the map versus the true geology that's derived from the impacts might not quite always reflect the same. And not just to show off like, oh, I was at the bottom of Meteor Crater. This is me and my friend Anna at the bottom of Meteor Crater. And I chose these pictures specifically because they show the outcropped target rock, the target rock that's exposed from the impact. In this right here, you can see this beautiful, I think that's a double layer of the Triassic Moa copy that was then folded over, overturned. But you can see the outcrop here along the rim and then here behind us with the little astronaut right at the bottom of the crater. And like I said, this consistency, and it enhances this validation and comparison across scales and planetary bodies. So we, not me, I wasn't there during the initial conceptualization, but I've really become invested in the project. But we developed this schema to standardize the mapping of impact craters to, enhance this cross-validation and comparison. So we started with this schema is scale-based and based on the diameter, rim-to-rim diameter of these craters. So on a printed map, scale-based, on a printed map, any features that are less than 5 millimeters on the map, nothing less than 2 millimeters, because anything less than 2 millimeters is just too small. That's going to be below the threshold, the mapping threshold. That's going to be represented as a surface feature, as you can see here in blue, just a little linear feature. Features that are 5 to 16 millimeters on the printed map are represented by the single undivided unit, which includes all impact materials, ejecta, etc. And anything larger than 16 millimeters on the printed map is going to be represented by these multiple units. So what does that look like in cross section? For a pristine, complex crater, something nice and beautiful, you would map the ejecta. Then at the rim, that's when you would start the wall. And then you get to the floor, and you map the floor, and then you have the crater uplift if present, but obviously not all craters are going to show the same pristine morphology. They're highly variable. I have mapped craters that are rim only, these ghost craters that were talked about yesterday. And, not every crater has visible ejecta. I was shocked at how many craters I was mapping, and I'm like, I see no ejecta. I can't differentiate this. I'm just not going to map ejecta. And that seems very weird to me. But it's true, morphologies are different. So we have these base foundational units for these multi-unit craters. One of the things that's not in here because it's, going to be scale dependent, the size of the crater, et cetera, is also potential outcrops that you can see depending on how good your data is. So we intend to map this across body and scale. The schema was initially developed for the Moon and Mars. All the values were derived based on Mars. The Moon and Mars will show us our end members, with the Moon having often having pristine craters, and Mars often showing a lot of degradation and erosion. So testing on the Moon and Mars, this schema, and Mercury will allow us to control. Mars will be the control, but then we can also examine for the radius of the body and the scale factor, and then extend that potentially to icy bodies, which might require a lot more consideration just because of the plasticity of the material. The target rock also makes a difference. So this is what this ended up looking like for me. I mapped within the Sinus Sebaeus region. Sorry if I'm mispronouncing that. The quadrangle, so that this is a 1 to 5 million scale map. These maps are all different sizes because this is what they look like at their actual printed map scale in comparison. So this is my 1 to 5 million scale map. This is a 1 to 500,000 scale map, and this is a 1 to 50,000 scale map. Showing this region right here. You can see, just for context, Schiaparelli craters right here at the top. For the people who know surface of Mars, just a little context. So this is my 1 to 5 million scale map. There were 833 of those smallest surface features, these 2 to 5 millimeter. I know it's a little hard to see, but those are the little just black circles that are in there. On this map at 1 to 5 million scale, those craters are 10 to 25 kilometers in size. Anything below 10 kilometers is below the threshold, the map threshold here, and is not represented. These single units here, those are the 25 to 80 kilometer or 5 to 16 millimeter features. Mapped 400 of those in this region. And then these multi-unit craters, those are the greater than 16 millimeter, or at the scale, greater than 80 kilometers on the map. We had 34 of those. So then I took this region right here, and that became my 500,000 scale map. This is what it looks like at the when it was mapped in the 5 million scale. So this is what it looks like mapped at 500,000. And you can see how like this single unit crater becomes a multi-unit crater, et cetera. We add a lot of these smaller surface features, et cetera. And I don't have stats. I don't have numbers for how many craters we did because I didn't go through the database and remove my false positives and everything else. That was taking way too long. So I did not have time before this presentation. But this is what that ends up looking like, where you still have your multi-unit craters, et cetera, and single unit craters and surface features. And these values are now 1 to 2.5 kilometers for the smallest, 2.5 to 8 kilometers for the single unit craters, and then greater than 8 kilometers for the multi-unit craters. Then I took this region right here and zoomed in, and this is on the 500,000 scale This is mapped at 500,000, but this region, this is what it looks like mapped at 50,000. So this is my 50,000 scale map. These craters, our smallest features are 100 to 250 meters. Our single unit, where's a single unit? These are single units right here, are 250 to 800 meters. And then our large multi-unit craters are 800, greater than 800 meters. Oop, there we go. So when we were mapping, this is not part of the schema, but just things that we learned while we were mapping. I did not differentiate between degradation states other than sharp and degraded for this mapping. For this purpose, it was not relevant to map more than just those degradation states. And I thought it was interesting because that is when I really got into the whole mapping based on feelings. Sometimes I see a crater and I'm like, oh, that's sharp. And then I draw it as sharp. And then sometimes I see it as degraded. I'm like, oh, it's degraded. It's the same crater. And I'm like, huh, okay, cool. Multiple degradation states might be more useful for a real mapping project. But for this, it was mostly statistics and how does it actually look when you look at it full scale on the printed map.
You meant, how does the crater make you feel today?
How does the crater make you feel today?
Sometimes they make me feel very angry.
Yeah, yeah, and they're all degraded. None of them are pure. None of them are pristine. One of the things that we learned when we drew our single unit, and I apologize for not having figures on this slide. I think that would be useful, but I can go back to other slides if need be. I initially began mapping my single unit craters. So the single units include the ejecta, the rim, the interior, etc. Not having the rim mapped out as a surface feature also was not helpful. Showing the rim as a surface feature and showing that distribution of the ejecta in one direction or another, or whatever, was incredibly helpful. And I feel like going forward, almost all of my single unit craters will have that rim mapped as well, but that's something that is going to be author discretion. And I began, as you can see here, mapping just out. I just started mapping out ejecta facies because I'm looking at this map and I'm like, it would be disingenuous to just map this all as yellow. There are clearly different processes going on here. So I began mapping ejecta facies. That is not part of the schema, but it is something that, you notice. The schema really recommends simply just these multi-unit divisions between the different size parameters. So our initial results, I think, and my colleagues think, are generally encouraging. But this makes sense. This was developed based on Mars data. These size parameters that we chose were based off of Mars. So when I mapped Mars, it makes sense that they look pretty good. One of the things we talked about was adjusting that larger category from 16 millimeters to 10 millimeters on the 500 scale map. That would be the 800 or 80 kilometer craters would then, that threshold would go down to 50 kilometers. I would really want to see what that actually looks like, if it actually benefits the map. If I go back to that map, it's just very busy. And I feel like some of these larger craters in here might benefit, like some of the ones that are right on that 80 kilometer threshold might benefit from being broken into multi-unit. But this is something I think that we're just going to have to continue testing to see whether that's reasonable or if this is, good enough for our purposes. Yeah, would it improve the usefulness of the product? We don't know. We'll have to test it. So we knew that these thresholds and ranges would work for Mars, but will they scale across other bodies? My colleague Corey is currently mapping Mercury, and then we're both going to tackle the moon. So we will be able to test for the scale factor that might be based on the radius of the body. There might be a radius-based scale factor that we that we include. That is maybe a formula, an equation that just scales that across bodies. That would be, simple to implement. Okay, but I think the further out question will be, will this actually scale to the icy bodies? The data from the icy bodies also changes how well we're going to test this. So we'll start with the terrestrial bodies for now, the data that we have, see if we can come up with the scale factor, and then move on to the ones that have the different target rock. So of course, the schema, these standards aren't standards, they're recommendations to the community. It's like, hey, I just need a starting point. This is where I'm going to start. And of course, for the map author, it is going to change based on the goal of your map product, whether or not it's reasonable. This is a map that I had been working on of a sinuous rill on the moon called Rimaconon. And I threw this in here because if I tried to map with the craters with the schema on my map, I don't think it would be reasonable. This map, if I printed it out, is 4.2 by 4.7 meters. It's enormous. Thank you. And these craters here, I think I included the 500-meter craters, but I initially only mapped the kilometer craters because the craters weren't the point of this project. The point of the project was to look at the morphology of the rail and the volcanic history. The craters, if I mapped into the schema, would be 20 to 50 meters for the smallest features, 50 to 160 meters, and greater than 160 meters. If this smallest crater here is 500 meters, I can't imagine this whole thing being just pockmarked with craters when the point of this project is not the craters. So it depends on the goal, the scientific goal of the map product, and the reasonability for the author. So we completed Mars, which is great. We're still assessing whether or not we want to tweak some things, but we're going to complete our mapping of Mercury and the moon, introduce that scale factor, and then start to do some comparative studies and some statistical analysis of what we're actually looking at. Using Mars as our control, so Mars will be our, scale factor of 1, and then potentially scale from there if the schema as is does not work for the moon and Mercury, which we'll find out. Yeah, I can't believe I finished so quickly. I had 30 minutes. I also had 30 slides, so I'm shocked. I think I'm going to ask if anybody has questions, but I think one of my biggest questions for the community is just introducing this schema, and I can put it back up on the screen. Based on your experience, you guys are the experts. I only started mapping craters and paying attention to craters a few months ago. I am not an expert. You are the experts in the community. You look at craters all day. Does this seem reasonable? If you look at a map like this, is this a useful product for you at this size? If you were doing mapping, I don't know how many people in here do mapping and geologic mapping, but does that sound like a reasonable thing or a good starting point to then adjust based on your needs? That's my biggest question for the community. And I'm, with the USGS, we are testing standards, but the biggest thing that we ask is for community feedback because we're here to support the community. And yes, we can say, cool, we've tested this, we've gotten community feedback, we're going to publish this and say, hey, these are some initial guidelines that you can follow. If you're starting your very first ever mapping product and you're reading our planetary mapping guide, what can we throw in there to help our mappers get started? I remember my first mapping project, I was clueless. I had no idea what I was doing. And I'm like, how do I draw these? What scale do I draw these at? I have no idea what I'm doing. And having those standards, reading through that book made me feel a lot better about it. So just increasing that robustness, I think, improves the map product. So that's my big question to you. Please talk to me. Tell me what you think. And does anybody have any questions for me?
Online, but I will ask first in the room if there are any questions. You can go ahead.
What do you think your biggest challenges will be on icy bodies?
I have not worked on icy bodies. I know that the scale of craters is different on icy bodies and terrestrial bodies. I don't remember what the details are off the top of my head. But I think that, yes, we're going to have a scale factor, but that scale factor, I think for an icy target rock is going to be changed. Like, I think there's going to be a general, a decrease in the scale size for icy bodies. I think we'll have to map a few of them to see if that scales across all icy bodies or not just radius based, but then a reduction or whatever it is for non-terrestrial bodies. Yes.
Stuart.
How would this apply at, say, 1 to 30K, your lunar South Pole, where we see nothing?
Well-
Expect some of this to follow.
Yeah, no, that's a really good point. I have the numbers written down for the 1 to 30K because obviously, as part of LMAP, but I don't remember what those numbers are off the top of my head, and I don't have a calculator to actually do that math. I apologize. I'm trying to remember what they are, because one of the things that I considered for my Rimaconon map that I showed, that was a 1 to 10,000 scale map. I'm considering increasing it to 1 to 30K just for reasonability. I think that it does work at that scale. And it really, like you said, it depends for the moon. It might be different on the moon, right? I did Mars. The cratering looks very different on the moon than on Mars. My Rumiconon project was on the moon, so I'm very familiar with the large scale aspect of lunar mapping. This map right here is 1 to 50K. Changing that to 1 to 30K, I think you can still apply the schema. It would be harder for the moon because there's so many just tiny overlapping bodies. You know what I mean? Craters. I think it can still be applied, but I think I can really answer your question after we do the moon because I haven't done the moon yet at that scale. Yeah. Yes.
I was just gonna say, I think it's kind of neat to hear the word schema and standards are being developed. I think the community has kind of been crying out for that for a while. Does that put an impediment in the process though, where groups have gone ahead and defined maps and their standards are gonna be, their schemas are gonna be different? So you kind of have to bring them back into the fold, hopefully.
Yeah, and I think like what we do with the USGS and the Planetary Geologic Mapping group, we recommend. We're not going to say, this is how you have to do it from now on. Everyone has to conform to our standards. We're like, hey, this is what we've tested. We think this is reasonable. People are going to map how they feel is best for their maps. And if they have schemas that differ, that's awesome. Just knowing that, hey, we want something that has been rigorously tested and hopefully scaled across bodies that, we can give something that's just easy. Like, hey, these are the values that you can start with. But of course, it's based on what you want to do. Like you have to adjust for your purposes for sure.
Yeah, sometimes in a paper, you need to do a sketch map. And it's good to still go back and reference the standards,
Yes.
So, I mean, it's to your advantage personally, because it's more recognizable to the reader.
Yeah.
They don't have to, convert this symbols and whatnot. So
And
this is great.
one of the things that I've seen during map reviews is like, yeah, we do have these standards or suggestions. And then when you deviate from that, it's often good to have a reason why. It's like, hey, we're not mapping to these recommendations. We are mapping at these, values instead for these reasons. And that's usually, I mean, that's always good enough, but that usually even, puts the question into the mapper's mind, why am I doing it at this scale? Am I, if I'm mapping craters that are much smaller, does it actually enhance the map product? Is it showing what I need to show, or is this unnecessary detail? Is it over cluttering the map, or vice versa? Am I not representing the actual cratering of the surface because I'm only mapping craters that are a kilometer when you're looking at something like this? So just a reason for any deviation, I think, even just for the mapper for themselves, like, this is my justification. I think this makes sense. It's a good starting point. I think that's the point. But thank you. Yeah, my understanding is that there was a call and a need for, beginning to test standardized standards for crater mapping. So yeah.
I'm gonna take it to the questions online for a little bit. First, just a comment from Kelsey Singer. Says, great presentation, agreed. It's nice to have flexibility based on the place and purpose of the map. And then the first question comes from B. Guri, which says, hi, I probably missed it, but how is this schema different from how we currently map craters at different scales?
Yeah, if there is a standard for, if there is an existing standardized schema, I'm not sure what it is. I don't know if that's, based on different institutions or different groups or what, but this is the one that was initially suggested back in 2020 and then now picked back up from the USGS.
Next question online comes from Christopher Brooks, says, interesting presentation. I have two questions. First one, I understand your colleague is doing the work for Mercury, but can you give us any comments or thoughts at this point on that?
I have not seen those maps yet, so no, I'm sorry, I can't. We really wanted to have at least one of the maps, the largest or the smallest scale done for Mercury in time for PCC, but we've been very busy with other endeavors. It did not happen, so I'm sorry. I believe that's being presented at GSA though.
Yeah. So the second question may be moot, but I will ask it anyway. Have you any thoughts on updating the schema in light of upcoming missions? For example, with Mercury, we rely on messenger data currently, but Bepi Colombo is en route and likely to give us data.
Yeah, we are always, testing and retesting. Like I said, we've had 50 years of the data changing, the technology changing, the techniques changing for planetary geologic mapping. These are going to continue evolving and we're going to continue adapting based on the technology and the data that we, as that continues to evolve in the future. So yeah, we'll come back to this and we'll test it again when we have maybe better data.
One other question online, Namishka Mendonka says, amazing presentation. I want to know how you would go about distinguishing between a degraded and sharp rim. Is there a definition for mapping them? And from what I remember in the presentation, this was a subjective thing.
Yeah, no, it is subjective. I'm very curious to hear what everybody in this room and online also has to say about that distinction. So the schema is not giving recommendations for mapping sharp rims versus degraded rims. We included that symbology specifically as we were mapping. We could have just drawn everything as a solid line, but that didn't really make sense to me. I'd like to have some of those degraded versus sharp statistics. But like I said, as I'm mapping, I draw a crater that looks sharp to me one day and then the next day it looks degraded. I'm like, why did I map that as sharp? So I think that this schema is not going to be recommending degradation state. This is specifically going to be how to map as surface feature unit, single unit or multi-unit. But I'd love to have a discussion with people about crater degradation states. Yep.
Let's talk
We can talk, yeah.
for a lab.
Okay, excellent idea.
Christopher Brooks, by the way, says, excellent, thank you for your answers. And Mishka, so thank you.
Okay, thank you.